I'm an artist. All right.
Yeah.
So today, here's the plan. We're going to talk about chapter 9, molecular geometry, or the Vesper theory, which oftentimes I mispronounce and call it the Vesper theory. I mean the same thing, okay? Get over it. Vesper or Vesper stands for valence shell electron pair repulsion theory. I'm sure you all read that and we're ready. Yep. Seth, didn't you have that same shirt on yesterday? Okay.
Wait.
Ladies, remember when I said you had every skill and talent ever? I don't know. Oh, he did wash it? Okay, never mind. Back on the good list. Okay, so this concept right here, and tying balloons together are actually extremely similar. Extremely similar. Oh yeah, like unbelievably similar. Yep, that's why they were there. Okay, so we'll do the balloon activity pretty quickly, which will help us learn about electron domain and and then molecular geometry. It's not awful. I love it. So if you were going to tie two balloons together, just draw what you think they would look like.
If I were to tie them, like
tie them.
with a string?
No, you would tie their knots together.
Oh.
Sorry. Like tie their ends together. Okay. What do you think? Whoa, Libby's got it.
Libby's amazing. You know how awesome Libby is?
I do know. She's pretty amazing. All right. Just a few that I can see. You'd have like the knot. And then I'm going to go sideways. Then you'd have a balloon right here. And where would the other one be? Sorry. It'd be directly apart or across from it, right? Is there any reason why it would be close? No, like that doesn't make sense. We'd have to put work in to make them closer. But they would be as far away from each other as possible, wouldn't they? Yeah. If you had another one, would they just all of a sudden be like, no, they look like that. Okay, moving on. So what you're going to do, the balloon activity. Hold on, we'll come back to this. You're going to tie balloons together. Now, I only have like 5 groups of 6 because I didn't go shopping. I went shopping and I forgot. Anyway, moving on. So you'll have to get big groups, but you just tie 2 balloons together and you draw the shape. You tie 3 together and you draw the shape. 4 together, draw the shape. 5, draw the shape. 6, draw the shape. Yep, just in a nice little column like this. So you'd have like 2, 3, 4, and then you'd have you like this shape, right? And then this one. I'm making the shapes up. They don't really look like this, but leave space because you're going to put stuff here.
Oh,
easy enough.
Should they be like 3-dimensional drawing?
The best you can do.
Wait, so how many balloons are we doing?
6, but we don't have one. We don't draw one not tied together.
Oh, that makes sense.
So 2, 3, 4, 5, 6. Any questions? Okay. So go and tie and draw, and I'll give you 10 minutes. Ready, set. Hey Siri, set a 10-minute timer, my friend.
There's 24, not 25.
It's fine.
10 minutes, starting now.
Are we just
All right. I know this is not very COVID friendly, but we'll be all right. All right, I dedicate this song to Seth, and because someone said the word cheeseburger. I only have a few spares, so hopefully you don't pop. They're over there. We're in trouble. What? You don't like this song?
I would have thought of anything else. I'm over here if I can hear.
Hey, quit being annoying with your balloons. Okay, some of these have been sitting in a drawer for 2 years, so maybe you got the bad ones. What?
There's a hole in it.
I'm running out of spares. Hey, we might need to combine teams because we got a lot of holy balloons. Are they gone? Okay, pair up. If you have to group up with someone else, it's okay. How's it going?
Good.
Good. Oh,
If you need me to do something, we'll let
I
me know
do
because
not.
It's not your problem. I'm just like
Nope.
ahead of it.
I'm solid. Thank you, though. What?
There's a lot of bullying happening in the class right now.
No bullying. I'll call your dad.
Oh no.
Did they pop?
I have 3 balloons left.
All right, find a group that needs them because they're just disappearing.
It's been too long.
It's a classic.
Because I literally only ever watched I only watched Little Einstein. Ninja Turtles.
How weird are you? Hey, we have some people they've lost some balloons, so if you need, just pair up. What? They play football out there every B time and lunch. It's crazy. Why? How we doing? Wow, pretty good. Yeah, if they're not the same size, it gets a little bit whack, but it's okay. It'll work. Is anyone afraid of popping balloons? Okay, I was just worried because Samantha's pencil's right underneath the balloon. It is kind of hard.
This is acceptable.
Sure.
Where does the 6th one go?
I have a thought. I know where it goes. Right there. It'll fit. It fits 6, I promise. Okay. Oh, that's kind of cute.
Everybody have this one?
That just looks like a corporate flower. Exactly.
Beautiful.
Just looks like a very.
Yeah, I must have been too.
I see.
That looks more like what?
It looks like a baby rather.
There you go.
There you go.
Right, 7.
Perfect. No.
Why not?
Merry Christmas.
So I would just like to notice that everyone else popped the balloon while we did not.
Some of them got balloons that had sat for 2 years instead of just one. Yeah. Oh,
I'm glad that that's realized. All right, there's 6. Beautiful. Dude, I am really impressed with you.
Okay, Thomas did the last one.
No, Davis did all of it. That's exciting. There's one red.
See that is our.
Looks like a fast fire.
it's hard because how do you draw that?
What's it called? What are they called?
This is what it always.
All of you.
The things that you put on the ground and then you bounce the ball and pick up?
Oh, jacks.
Yeah,
Yeah.
they look like one of
We
those.
play giant jacks.
We have giant hands.
I believe they're the same.
Is this how I
4 things and then 1 and 1. The jacks.
I like the one that I just saw.
In this model, what are the people?
That's pretty good.
So where are your pajamas? Let's go spirit.
I know. I sleep in my underwear. So
That would be hard.
what? I am a Grinch, so I should get some. Okay, once you're done, maybe one of you takes it back to your desk. It's beautiful, Bill. All right, we had two survive.
Or maybe they just have holes in them.
Maybe. Not yet.
Not yet. No.
You messed up.
I can,
There's no air in here, so.
I'm a little confused on why all 3 of them ended up with males.
I asked for it. Tim wouldn't give.
No reason.
Bullied.
I feel like that's gonna pop.
Okay.
Tim, I love your hair.
Tim's hair is always perfect
Wait, how did it not get messed up? That's so fair.
because his name is Tim.
Where does it happen?
Anyone with a T, a vowel, and an O in their name is awesome.
I have none of those.
TOM.
I literally don't have a single one of those letters.
That sucks. Okay, are we ready? This is a goofy activity, but it literally shows you everything I need you to know to start this whole process. All right, when we tied 2 balloons together, it should have looked like that. Unless you're weird, somehow you put in force to make them bend. Are you okay with that?
Wait, what?
All right, I want you to put right here 2, and then I want you to put ED, electron domains. And then I want you to write the word linear. This will hopefully all make sense in the end. So when you have 2 balloons, they made a line. Okay, the bond angle between this atom and this atom is 180 degrees. So put that right here. So far, so good. I'm going to move, but it'll still be there.
Okay.
Okay, then you tied 3 balloons together, and it looks something like that, correct? In whatever orientation you feel like, it looked like that. Okay, I'm going to say this has 3 electron domains. So here's something you should kind of know from now on. An electron domain is like a balloon. It's the thing that occupies space. Balloons, when you tie them together, they stay apart because you tied them at the knot, and then they occupy the opposite space, right? Electrons, when you share them, they dislike being by each other. So where do they want to be? As far away as possible. So if I have 2 electron domains, that means 2 places the electrons live, then they're going to orient themselves as far away as possible. If I have 3, I have this structure, all right? And we call it trigonal. Now, trigonal, the angles between the 3 is no longer 180. Any guesses?
100.
It's 120 degrees.
Oh, man. Who said they were close?
Corbin. I have scored the test. Well, I haven't actually scored them. I've marked them for your redoing. One of you got really close to a perfect score, and I'm just looking for like one main word. Some of you hurt my feelings. Like I got the most wrong answer I've ever seen in all of chemistry on this test.
Oh, no.
Oh,
You should tell us.
Yeah.
I'm really happy to have it.
I won't, but I was so offended in every way. I'm like, you couldn't be more wrong. Don't worry, I didn't write it. I just felt it. Okay, no,
Which question was it on?
I'm not. Oh, okay. Let me make fun of someone. No,
No, which question?
Which question?
I don't remember.
How do you not remember if it was the most wrong answers?
Okay, I do. I'm just, yeah, thank you. Okay, then it got harder to draw, right? Because then it went 3-dimensional.
Then it went weird.
But that's okay. If it has 4 balloons, it has 4 electron domains. We call this tetrahedral.
Tetra.
It's one word. I just needed space. Tetrahedral. If you H-edral. Who's smarter than me? H-E-A-D-R. Yeah, there's reason.
It's hedral?
Hedral.
H-E-D-R-A-L.
Okay, now
Thank you.
this one's weird because now we're occupying like a volume. So you'd think, hey, I just took 360 and divided it in half. I took 360 and divided it in 3. I'm going to take 360 and divide it by 4. No. Mm-mm.
Sadly.
Anyone know this? Bill, did you read ahead?
No.
He's so let down with himself right now.
No. I knew it was gonna be like something weird.
109.5.
That's for all of them?
Math. Okay, because if you think about it, remember you had one that kind of went up and then 3 that bent down and away from each other. And any way you spin that, you're going to have 1 up and 3 that point away.
It's just so hard to draw
Right.
arrows because it's like,
You don't have to do the arrows. Draw what arrows? The angles?
yeah,
You don't, that's,
well, I do.
okay, sorry. She's a perfectionist. Okay, then we got to 5. 5, what'd that look like?
It's like,
Okay, same thing, but one at the bottom?
yeah.
Pretty kind of.
I like this is, wow.
You're an artist.
I don't even try.
It's so fun.
I have a picture of it, we'll see. This has 5 electron domains. It's almost like it was 5 balloons tied together.
What's this one called?
I don't remember. It is, I remember now. This is called trigonal.
What?
Don't argue. bipyramidal.
What the?
Trigonal, bipyramidal. It's two pyramids on top of each other. There you go. Dang right.
Wait, this is 5 balloons. Oh, I get it.
Don't worry about it.
Okay. We got it. I
All right.
I just-
Now this one. This is different than all of them so far. Because in trigonal bipyramidal, we have some that go up, right? I can do a better job now. And then the ones that go around the middle, correct?
Yeah,
So not every angle's the same.
yeah. Really good.
We're going to have a 90-degree relationship.
Holy shit. I'm so smart sometimes.
Happy, I wish I was as smart as you are.
Thank you. No, you don't.
Okay. Then between the three around, I'll put them in green.
Oh my heck.
Around these, you'll have a 120 again.
Oh,
Look
okay.
at Kristen.
So this one you have 90 and 120.
This looks really good.
All right, now we're going to learn a couple words here. They'll come up later, so don't stress. But this, in this trigonal bipyramidal, the 90-degree are for your axial angles. And any super geniuses want to guess the 120s? What? Nope. Nope. They're all good guess. This is called equatorial. So like our planet, the axis is what goes through the top to bottom, and the equator is what goes around the middle, right? So back to this picture, red would have been axial because it's the angles between the axis and the bombs with me. And then green would have been equatorial. And it's the interaction between the three around the equator, those electron domains. You all right with that? That's what I was thinking. It's like, oh, third hair, gross. Just kidding, I have no idea. Okay. What? 120. And it's the ones that go around. Okay. And then finally we had 6 balloons. And that had an up, a down, and 4 around it, right? That means all of them will be 90 degrees.
Hallelujah, it's a miracle. And there's 6 easy, whatever that stands for.
All right, this one makes me mad too. The name of this one, I don't like it either. Are you ready? No.
No.
Oops. It's called octahedral,
No.
but it's not 8, but it is.
No.
It is.
The world is wrong.
I'll show you. It's because it has 8 sides. Timmy?
3 sides or like 1, 2, 3, 4,
Wait, how do you see that?
5, 6, 7.
They're there. So 1, 2, 3, 4.
Oh my.
And then 5, 6, 7, 8.
I don't like that.
How'd I do? Sorry, I was stupid. All right. I've just announced a lot of games where people yell 5, 6, 7, 8 right in front of me. So it has 8 sides. I know it has 6 things, but it has 8 sides. 4 on the top, 4 on the bottom. I don't like it either, but I didn't get to choose it.
Like 8 triangles.
If you want to look at it that way, absolutely. Okay, octahedral. And then all the angles are 90. No matter what way you spin it, they're all 90 degrees to each other.
90 degrees.
We all right with that? Okay, these are your 6 basic electron geometries, and they are just like tying balloons together. Electron pairs push each other away. They want to be as far away as physically possible, just like when you tie balloons together, they push each other apart naturally. Are you okay with that? Okay, electron domains I should have written this, I guess. I never did a table. So this would be the electron domain geometry. That's what all of these are. The electron domain geometries. We okay with that? Okay. This is the number of electron domains. And we're good with that, right? Okay. And then this is the name of the electron domain geometry. And then these would be the bond angles. He must have heard me talking crap. All right.
I'm either gonna spell angle or angel.
Yeah. But did I spell it right?
I hope so.
Yeah,
Because I
yeah,
feel
yeah,
like
you did. You took the
46 years. I finally got one right. Sometimes. I did one either today or yesterday in some class again. Like, all right, we okay with that? Okay, looking back here for a second.
it's like ready to pop.
Look right here, everybody. We just did this. Now there is molecular geometry, and they are not always the same. It's not bad. This is not an except. This is like the electron geometry shows the location of all the electron pairs, bonding and non-bonding. Molecular geometry just shows me what it looks like. So here's an example of what I'm talking about. And we'll go through notes, so don't think, oh, I'm lost. I know. So if I do the Lewis structure for oxygen, I have H, a line, an O, a line, and an H, and it had these, correct? You all right with that? Okay, look at me. I mean, look at the screen for a second, not me. We would look at the central atom and look at the screen. I would say I have one. That's an alien. He's looking over here. Okay, I have, look at, sorry, I have such bad, I cannot focus. But it is, you see it, right? He's looking right at you, no matter where I go. Okay, here we go. Look at the screen. I have 1, 2, 3, 4 places where electrons are located. 4 places electrons are located, which means it has 4 electron domains, which means it is tetrahedral. There you go. And that's why water, tetrahedral looks like this, right?
Oh my God.
Whatever. And that's why I've always drawn water as an O with an H and an H, because I had these up here that were pushing it away. You with me? It's 109.5. 109.5. Now look, this, and I know this is ugly, but you kind of know what I'm talking about. This is the electron domain geometry, and this would be the molecular geometry. These circles wouldn't have been there. That was just a talk. These, neither would those. Neither would these.
The world makes sense.
Okay, now, when we talk about this, we'd say it's tetra. But does the molecular geometry look tetra? No. Water has its own structure. Well, I mean, there's more that are. That was stupid. We say this is bent. Bent. we would think they'd line up in a line, but it's bent. Okay, so they're not always the same. Now, stick with me just for another minute. You guys are doing great. If I had methane, methane is CH4. If I were to draw the Lewis structure, it would look like C. Let me just do it with lines. That'll just save me some time, which is the way it's supposed to be anyway. It would just look like this, right?
Yeah.
Now, how many places do electrons live? 1, 2, 3, 4. So what structure would this be? Tetra. I'm not going to spell hedral, but tetrahedral, which we would mean, or we would think would look like 1, then 4 kind of bent, but around it. You with me? Okay, here's my octopus with a mustache. Okay, he's French. You with me? Now this would be the electron domain geometry. And this time, wouldn't it be the same?
Oh, that's why it's always drawn so weird like that.
Yeah, they like put a little wedge thing, right?
Yeah.
Like 3 dimensional.
It makes it look
Mhm.
so weird. I was, why don't they just make it like
Whoops.
square, like it looks top?
Okay, so you kind of with me?
Okay.
So in methane, the molecular geometry and the electron domain geometry were the same. Tell your partner why they were the same in this one. If you don't know, it's fine. Just go ahead.
You hear that, Nathan?
Yep. Okay. These two, I think, said something right. They said something like, well, in this one, all of them were bonding. Is that what you heard? I heard, I mean. Okay. And in water, were they all bonding? No. So the electron domain geometry accounts for everything. The molecular geometry only accounts for where the bonds are.
Oh.
Okay, I'm going way ahead, but that's okay. If I were to draw CO2, I would have an O. You should hopefully remember. I'm going to put an arrow. That's going to be confusing.
I can tell you.
It would look like that, correct? All right. How many places are there that electrons live? It's 2. It's 2. Let me say this. How many sides have electrons on them for carbon? Just 2. So a double or triple bond still is just one place that they are. So carbon dioxide looks like this, right? Whoops. It has the 2 electron domains, whatever. That means it's linear, right? And so let's look the exact same.
Oh.
Right, so we're basing all of this off just
The central atom. Yep. We will eventually, like tomorrow, have like CH3OH.
Ooh, that looks not bad.
No, it's really not bad. You have CHOH. And you're like, okay, this piece is tetra because there's 4. This piece is linear because there's 2. This piece is, oh, sorry, that's actually bent. Sorry. And that's bent. Well, I'll show you, but we can eventually do it when we combine them. Okay. All right. I've skipped way ahead. Let's just talk some words now. You okay with that? Our goal is to be able to draw and label the electron domain and molecular geometries of molecules. We're close, actually. We're really close. If you don't want to hold the balloons anymore, you can just chuck them on the ground. Not yet. Okay, so chapter 9, note time. Chapter 9 has one huge topic and 2 minor topics. We're like halfway through the huge topic already. It's called the separ, or valence shell electron pair repulsion. The balloons are representing electron pairs. Easy enough? All right. Then polarity based on geometry, hybridization, and sigma and pi bonding. It's not bad. Okay, here we go. So this is from the AP. They believe it is important that you know how to use the Vesper theory. All right, we need to know Vesper theory uses Coulombic repulsion between electrons for the basis of predicting the arrangement of electron pairs around a central atom. Coulomb's law is everywhere. All right.
Are we gonna like ever not need Coulomb's law?
After this chapter, we won't talk about it for a while. Like it's still there, but we're not going to stress it. All right, here we go. Both Lewis diagrams and Vesper, they tie together. That's why chapter 8 is before 9. Must be used for predicting electronic and structural properties of many covalently bonded molecules and polyatomic ions, including the following. So the molecular geometry, we just kind of showed you. I don't expect you to have it memorized. Bond angles, you do have to have memorized eventually, just not yet. Relative bond energies based on bond order. Bond order means, is it a single, a double, or a triple? And singles low, doubles high, triples highest. We went over that a couple days ago. Bond lengths, these two are tied together. All right, so like O double bond C double bond O, this is a shorter bond than if it was O to C to O, right? Double shorter, double stronger. All right, presence of a dipole moment, we've sort of talked about that. It's in this unit as well. Hybridization of valence orbitals of the molecule. We have not talked about this at all. You read it and it's super complicated, but I'll just tell you in a nutshell. What it says, like carbon should be 1, 2, 3, 4 valence electrons, right? But it doesn't do that when it bonds. It goes to C 1, 2, 3, 4. So right here, carbon would be 2 in the S, and then 1 here and 1 here. That's how it should be, right? That's how it is. But in a bond, a tiny bit of energy is absorbed and put here. So now carbon has 1 in every single box, which means it can form bonds with how many things? 4. When we promote this electron, we call this thing a sp hybrid orbital because I mixed the s's and the p's. Now, that's the nutshell. We'll do it again, and it's going to seem really complicated then, but that's all we're doing. What's that? That's all right. I got you. Okay, there's more here. That tells you the stuff you don't need to worry about. And then here we go. All right. The shape of a molecule, we went already over this, but now we're just doing the notes. The shape of a molecule plays an important role in its reactivity. Who would have known the actual shape of it matters? So if we are in chemistry and we care about how things react, then we must care about the molecular shape. And the shape comes from the electron domains, which come from the pairs, which come from all the Lewis structures. So we care about all of it because ultimately it has to do with reactivity. Okay. By noting the number of bonding and non-bonding electron pairs, we can easily predict the shape of a molecule. Like I think by today, you could do most molecules tomorrow. Because it's not bad. It's just, oh, well, what did the 4 balloons look like? Oh yeah, they look like this. Okay. Now, there are some words we haven't really talked about yet, like trigonal pyramidal, T-shaped. They're coming, but they're all right. Here we go. Whoops. Okay. So simply put, electron pairs repelling each other, by the way, whether bonding or non-bonding, repel. They repel, they repel. Now, this thing right here, I thought I had this, maybe it's on a different slide. When we say they push each other apart, that's also known as a Coulombic force. Coulomb's law says like charges repel, right? So if you read and it says the word Coulombic forces or Coulombic, that just means that they're pushing each other apart. Okay, so here we have hydrogen. Hey, just real quick review, how many electron domains? Tell your partner. 4. 1, 2, 3, 4. Tell your partner then, what is its electron domain geometry? Tetrahedral. Are all 4 of them bonding? No. So the molecular and the electron will be different. We haven't gone over this one. It's right here on the previous slide. It is a trigonal pyramidal because we had this and it pushed the 3 down, right? We'll now get rid of that one and it still pushes the 3 down. We just don't write it. N, H, H, H. The knot in your balloons is the central atom. Okay, so N would be in the middle. So we had a Coulombic force pushing the H's around, and that's why we end up with the shape. Okay, by assuming the electron pairs are placed as far as possible from each other, we can predict the shape of the molecule. All right, so we have talked about it. Here is your definitions, basically. We can refer to electron pairs as electron domains. In a double or triple bond, all electrons shared between those two atoms are on the same side of the central atom, therefore they count as one electron domain. Okay, so even though A is violating the octet rule, right? Because it has a double here, we'd still say it has 1, 2, 3, 4 places that electron lives, tetrahedral. Okay with that? Now it's molecular geometry, not because there's a non-bonding pair.
So the finger also includes, like, it compensates for resonance.
When you do resonance, it won't matter on electron domains at all. Because it's just really, I don't love how this puts it. It's from the book. Electron domains to me is just the amount of places around the central atom there is things. And there are 1, 2, 3, 4 places.
It doesn't matter how much.
Doesn't matter. Now it'll matter for the shape of the cloud later. And we'll say, hey, a 109.5 in this situation is really a 107. But like, you don't have to have that memorized. Like a double bond, it does affect it, but not something we need to stress about. Okay, here we go. Draw the Lewis structures for the following: CO2, NH3, SO3. We've already done 2 of them, like in the notes. You didn't maybe draw them. And for each, tell me how many valence electron, or sorry, how many electron domains there are around the central atom. Ready? Go. Oh, the Bensons, this whole time I didn't even know you were there. I am sorry, Bensons. The balloon activity probably made no sense to you. But we tied balloons together and it was marvelous. They came out like this. You're welcome. It is absolutely beautiful, like my face. Are you kidding me? Where does the time go? Seth would like to argue that he's tireder. You're welcome. I'm glad you enjoyed that. Okay, for speed purposes, I got it done. Tell your lab partner which one of these has a resonance structure. SO3, right? Because that double bond could have been anywhere, correct? Okay, how many electron domains in SO3? 3. All right, how many in NH3? 4. And carbon dioxide? 2. All right, this one, pretty easy. I'm going to say it's linear. This one should be tetrahedral, but it has a non-bonding pair. we're going to learn that that means it is trigonal, pyramidal. Means it's three, but they're pinched closer to each other. And then, all right, this is its molecular geometry. I better be careful there because its electron geometry was tetrahedral, right? They're tricky. Mostly, by the way, we just care about molecular geometry. But to find out, you need to know its electron domains. Three. So would this be trigonal pyramidal also? No, this is trigonal. Whoops, whatever. Trigonal planar. Yep, all three of them were all arranged on the same plane. Okay. All right. So if I had, we only have two here, and those probably have holes in them. But if I tie these two balloons together here, the third one is going to be right here. And they're all on the same plane. On the other one, there was a fourth one here that pushed them down. So they were a little closer. Does that make sense? Okay. All right. So here we go. I feel okay about that. Oh, hey, this is where it was. This probably should have been way at the start. But the best arrangement of electrons is as far away as possible because they repel. And once again, repulsions are referred to as Coulombic forces. We're almost out of time in here. I got close. I mean, I'm within 20 minutes of where I want to be. Did you say props? Well, people write things down. That's what kills me. And it's fine. I'm not complaining. All right. I'm going to skip that. And I'm going to skip that. Okay. So here it is drawn by professionals. It's basically what we've said. 2 balloons, linear. 3 balloons, trigonal planar, and 120. 4 balloons, tetrahedral, 109, 120 and 90, and all 90. You see the pyramids? Like,
Why did you draw those? For the trigonal pyramidal, bipyramidal, how do we decide which one is going to be the axis, which one's going to be the?
you'll learn. It's fluffy, but we'll go over it. Okay, these have to be memorized. You have to know the names, and you have to know the angles, and you have to know the shapes. Okay. All right, to do what we need, all we got to do is count up the number of electrons in the Lewis structure, the geometry in that which corresponds to the number of electron domains. We did that at 10 times. I've been commanded to speed run. So once again, NH3, we draw it. We count the domains and come up with tetrahedral. We find a non-bonding pair, and then we draw the molecular geometry. They are bent away because this electron pair pushes them away.
Take a little face. Yeah, it's like the arm.
No. You're welcome. Okay. Now, this is where we'll start again tomorrow, but within each electron domain, there might be more than one molecular geometry. So there's actually more to memorize. So tetrahedral has tetra, trigonal pyramidal, and bent. Go ahead. If you want to pop some balloons, that's fine, but you got to pick up all the garbage. All right.